Thank you. Well, I want to thank the organizer and all the other helper for inviting me for this very nice event. I've heard a lot about and I hadn't been able to attend before. Mm. So the context is representation theory of quantum affine algebra, but more precisely quantum loop algebras, which is, well, in this context, not that different. So the quantum loop algebra, it's not completely necessary to understand all the relations and definition of the quantum loop algebra for this talk because we're only interested in representation theory of it. But just for completeness, you start with, and it's type A quantum loop algebra. So you start with a type A Lie algebra that you affinize it. So you add in some affine, some t variable and you affinize the generator that way. And then somehow you quantize it in the generic case, so Q being not the root of unity. And so as I said, we are interested in representation theory and in particular finite dimensional representations. And basically, this representation theory would look a bit similar to the representation theory of the affine Lie algebra. So in particular, well, as usual with representation theory, we are particularly interested in studying simple representations. And in that case, there are highest weight representations. And the highest weight will be loop weights. So instead of, in the classical case, you have fundamental weights, omega I for I node of the Dinking diagram, so 1 to n. And in this case, you have a loop version of it. So for the combinatorial part, it's going to be a segment AB with integer endpoints, where I, the node of the Dinking diagram, is the length of the segments. And you have another parameter, which is this affine parameter R, which is encoded in the middle point of the segment. So midpoint of segment and length of segment is encoded in a segment. So a dominant weight, instead of being a sum of fundamental weight, it's going to be a multi-segment, so a sum of segments. So for example, instead of having this sum of this dominant weight 2 omega 1 plus omega 2, you can have the multi-segment 1, 1 plus 2, 2 plus 1, 2. So of length 1, 1, and 2. And as usual, as I said, we want to have information on simples, but as usual, this is a difficult problem. So what is easier is to study Weyl modules. So they are indexed by the same thing, by multi-segments, and they're defined that way. So for a multi-segment sum of multi-segment M, you construct the Weyl module by just taking tensor product of the simple modules associated to each of the terms. So it would be the fundamental blocks of the category. And so those are really, really easier to study, and it's not that difficult to go from one to the other because they also form a basis of the Grothendieck ring, and there is a unitriangular change of basis. So it's easier to invert and go from one to the other. So for a small example, if you have this multi-segment 1, 3 plus 2, 5, also represented like this, then the Weyl modulus is this tensor product. It's not simple. It has well, this is everything in the Grothendieck ring, but I just removed the classes so it's easier. It has two parts, so the highest weight module of the same weight, and some other simple, which is this one is actually equal to the corresponding Weyl module. So it means that if you reverse everything, reverse the system, this simple representation can be written as this alternating sum, or as this determinant. So it's this term times this term minus this term times this term. It's really a 2x2 determinant. So that's a nice formula, and the type of formulas that I want to get. So because first of all, if you can write a class of a simple representation as a determinant like this, well, it's a closed formula, and then you can have interesting relations because it's a determinant. So when can we do that? There's a historic of which representation can be written like this as a determinant. the first one from the 90s, but the first time it's actually written in kind of this context was by Lapid and Minguez. And they wrote it for representation that are called snakes modules. So that's multi-segment that satisfies this relation. It will look like kind of like a staircase because everything is well ordered. And in that case, the simple can be written as a determinant just by exactly putting all the mixing the endpoints of your multi-segment like this. And then the result I prove is for a bit more general. So it's for regular multi-segments. So it means that all the endpoints just need to be different, but not necessarily well ordered, and also real, which is an important condition that I'm not going to detail here. But in that case, you can also write your simple representation as a determinant of a matrix, which is almost just taking the fundamental corresponding to the specific endpoints, but sometimes you have to add in some zeros. Have to know where to add some zeros in the matrix. And this is based on an alternating sum formula written by Lapid and Minguez. And since then, there have been recently some work of Brito and Shari for stable alternating snake modules. So it's another generalization of snakes, also technical definition that I'm not going to give. And it's also, they can also write the simple as a determinant with some zeros added in at some specific points. And that's very different method than the one presented before. So for example, this is an alternating snake module. You can see that it's alternating snake because it kind of goes like this. It's ordered and then change direction and then change direction again. And the simple associated to that can be written as the determinant of such a matrix with some zeros that are shaped like this, just to give you an idea of what the kind of places of the zeros look like. So as I said, so that's nice closed formula. And as I said, it's also interesting that because we can use relations on the determinant. So there's lots of relation you can write on the determinant. The one I'm going to be interested in is the Lewis Carroll identity. So it's if you have a n by n matrix, then you have this relation. So it's this is always the matrix, and here is you remove one line and one column. So if here you remove one line and one column, here you remove another one. Here you remove both pairs of line and columns. So this determinant times this equals this times this plus a term where you're mixing the pairs of lines and columns that you're removing. And for those who know, this looks like a cluster algebra relation, and it is often a cluster algebra relation, particularly in this context. So if you apply, in a very simple case, if your multi-segment is just some sort of very clear staircase like this, and if you apply this relation, then you're going to get something like a relation that looks like this. So in that case, the simple can be written as a determinant, and you remove the first line and first column, and the last line and last column. So what you get is the simple associated with the segment when you remove the first one, and the one you remove the last one equals the full thing, the one when you remove both first and last, and then a mixed term where you actually get something and you join the endpoints that way. And this is actually a well-known relation called the T-system relation. It was established by Nakajima in the early noughts. And it comes from it's an important relation in the quantum integral system side of things. It comes from a short exact sequence. And it actually corresponds to an exchange relation in some cluster algebra structure associated to this category of representations. There's a slight generalization of that for snakes. So this was the condition for snakes. So it's just kind of the same thing, except the lines are not all the same length. And this gives you the extended T-system, which is also a well-known relation that pre-exists this consideration. And we know that it comes from a Scheit exact sequence, but it's still unknown that it corresponds to an exchange relation in the same cluster algebra structure. Yeah, this is what I did. It's not, this is from Bittmann. So for real regular, we have the same kind of relation. But in that case, we don't know that it comes from a short exact sequence, and still don't know that it comes from an exchange relation in cluster algebra structure. But we have a similar nice generalization of a relation like this. And the next step is for alternating snakes. Since now we know from this year that it has a determinant formula, can we write can we write such a relation to get a new family of relations in these simple representations? Thank you for your attention.